Hello everyone. So we're going to talk about the um, basically a 4-bit adder that will add a 4-bit binary number to another 4-bit binary number, and then it will give us a result of 4 bits, and then a carry out if there is any carry out. Now this carry out is very important. We're gonna talk about that later. Now. Well, basically, we are going to build this using the very basic elementary gates, and not any complex ones. So, for example, here um, I've mentioned an XOR gate, right? So instead of using any XOR gate here, I actually built it from scratch using some elementary gates, basically, and an OR and not gate. Now, the adder itself will start as any adder will start by a half adder for the first bits, and then a full adder for the last 3 bits. Now these adding operations are actually sequenced. So the second, for example, the second add operation will need the result of this carry out of A0 and B0 in order to complete. That's why, for example, we cannot perform the second operation until we somehow finish the previous one. And this is basically make these gates a little bit slower, but the implementation the implementations that are actually available at the moment are much faster, where they can basically, the idea is that the adder itself can predict beforehand, can predict if there will be a carry out or not, and if it expected a carry out, then it will wait. Otherwise, it will just do the adding operation. So we start by the first bits, right? They entered into an XOR, and this will give us the sum of the first 2 bits, and then these 2 bits are actually entering an AND gate. This AND gate will give us the carry out of 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 this first operation. Then the carry out of the first operation entering, entering the basically the second operation will start by adding the first index or the second bit of those 2 numbers. Then they enter the XOR as usual. Now this XOR will need to be XORed as well with the carry out of the first operation, and this will give us the sum of the second operation. Now the end of the carry out of the first operation with the sum of the second operation in here are going to enter an OR with the carry out of the first operation. This will give us the carry out of the whole operation itself. This carry out will enter the third operation. The third operation start with an XOR, and then it has a carry out. Now this the carry out of the second operation will enter similarly, will enter an XOR with this gate, and then this will give us the sum of the third operation. Now this carry out actually is going to enter an OR with the carry out of this operation, giving us the carry out of the whole third operation. Now the last operation is also important. It's basically going to do the same, but the carry out of the third operation or the last operation is actually going to represent the carry out of the whole operation. And this carry out in particular is very important because if you have a carry out, and if your system, for example, have can maximum represents a 4-bit, and then you have a carry out on this operation, that means the result is actually a 5-bit binary number, which if your system cannot represent it, then it's an indication of an overflow. Otherwise, this depends on how the system can operate the result. If they can represent, for example, a 5-bit, in this case, a 5-bit a number, then it's gonna be normal. Otherwise, as we said, is gonna be an indicator of an overflow. Now, the sums of each of these operations are actually giving us the for example, the x, which is the result, the 0 and 1, 2 and 3, basically 4 bits of the result with the carry out. And this is the whole thing about the other the 4 bits other. Thank you.